Hello everyone, we are from Group 2 and today we would like to present our mini project titled Smart Heart Monitor. Allow me to introduce myself. My name is Raymond Surya Anggoro.
My name is Vanessa Laura Haryanto.
And my name is Christopher Matthew Setiawan.
So according to Central Centers for Disease Control and Prevention in 2020, approximately 670,000 deaths in the US are primarily caused by hypertension. Additionally, according to a population health survey done in Hong Kong, 27.7% of people was diagnosed with hypertension, whereas 47.5% of them have been undiagnosed before. That just goes to show that it is essential for people to regularly monitor their blood pressure. Therefore, the Smart Heart Monitor aims to give the opportunity to people to monitor their own blood pressure so they may determine their current health condition and prevent things from going to worse if were to be detected an anomaly in their blood pressure. We would also like to give the benefit to the users to keep track of their previous recorded systole and diastole such that the user can display and compare the current one with the previous one.
Next, I'm going to explain the foundation of the blood pressure. The blood pressure is the force of blood against the artery's wall and is detected in two numbers. The first one is the systolic blood pressure, is when the heart beats or when the heart muscle is contracting. And the second one is the diastolic blood pressure, is when the heart rests between beats, is when the heart muscle is relaxing. Next. Next, I'm going to explain the blood pressure range in the table. In the table below, the normal blood pressure range is 120 over 80. The 120 value is the systolic and the 80 value is the diastolic. And the hypotension blood pressure range is less than 90 over 60. And the hypertension blood pressure range is greater than 140 over 90. Next. In the principle of the blood measurement, the blood measurement is measured in the millimeters of mercury or mmHg, and the readings are given in pairs, the systolic value and the diastolic value. The systolic value is written first, and then there is a slash, and then there's the diastolic value. For example, it's 120 over 80. The systolic value is 120 and the diastolic value is 80. And the device to measure the blood pressure is called the sphygmomanometer. Next. The sphygmomanometer, there are two types of sphygmomanometer. The first one is the electronic or the digital version, and the second one is the manual version. The electronic version is shown in the top picture, and it can display the blood pressure readings digitally, and also automatically detect the systole and the diastole. Meanwhile, the manual one requires the user to pump and release the air into the cuff by themselves, and also the readings is given in the dial. And basically, how it works, sphygmomanometer is when a cuff is wrapped around your upper arm and it is inflated until no blood can flow in the brachial artery located in the upper arm. And the systolic blood pressure is detected is when the first heartbeat after the cuff is slowly deflated, and the diastolic blood pressure is detected when the stop of heartbeat when the cuff continues to deflate. This is the oscillations in cuff pressure. We can see in the first one, the systolic pressure is when the heart beats after the cuff is slowly deflated. And then the diastolic pressure is when the heart rests between beats and at the end after the cuff is deflated.
So as we can see, in here, we want to understand the principle and the background of blood pressure measurements and the sphygmomanometer. And we also want to understand the connection between sphygmomanometer with the microbit and the jumper board, which aims to implement the principle of blood pressure measurement. And we also like to produce features on blood pressure monitors, which can show the systolic and diastolic pressure and can warn the users about the condition of their current blood pressure. Next. The apparatus and materials that we used are microbit version 2, lab kit, power supply, air pump or valve kit connected with speak mode manometer, jumper wires, and USB Type-B.
Next, I'm going to explain the lab kit connection. We're using three devices, which is the microbit, the jumper box in the lab kit, and also the blood pressure sensor. The microbit and the jumper box is connected to the 8-connector breakout board. And the microbit, the pin 15 is connected to the R LED input in the jumper box to power the red LED, and the pin 9 is connected to the green LED input to power the green LED. And also the pin 19 is connected to the serial clock line, and pin 20 is connected to the serial data line. The serial clock line or the SCL and the serial data line or the SDL is used to power the OLED display. Next one, the pin 3 volt in the microbit is connected to the plus 3.3 volt in the jumper box, and the pin 0 volt is connected to the GND in the jumper box. Then the blood pressure sensor is placed in the breadboard and the lab kit, and the 3.3 volt pin in the blood pressure sensor is connected to the plus 3.3 volt in the jumper box. The GND pin is connected to the GND in the jumper box, and the 5 volt in the sensor is connected to the plus 5 volt in the jumper box. In the microbit, the pin 0 is connected to the heartbeat output in the blood pressure sensor. The pin 1 is connected to the blood pressure output in the blood pressure sensor, and the pin 8 is connected to the air pump input, and pin 2 is connected to the air valve input. The pin 8 and the pin 2 act as a air pumping and air releasing automatically. Next.
So the first features are LED lights. So we connect LED lights, red LED lights, to indicate the hypertension or hypotension disease. We use red dot right analog function. And we also connect green LED lights to indicate normal blood pressure. Next. The second features is speaker. We connected the jumper board with the speaker to output hypertension sound to indicate hypertension, hypotension sound to indicate hypotension, and normal sound to indicate normal blood pressure. Next. Our third features is to display text on the OLED. So after the measurement, we will display the blood pressure measurement number on the OLED. And after that, it will be followed by the systolic and diastolic pressure number. And after the second measurement, we will display the previous systolic and diastolic pressure number. And when the measurement indicates hypertension or hypotension, we will display the hypertension or hypotension text. And after that, we will also display some suggestion text such as exercise, no smoking, go to doctor, and etc. But if the measurement displayed indicates normal blood pressure, we only display normal text. And after that, we will display a little stem on the OLED. Next.
So in the feature 4, we use microbit 5x5 LED, which displays an image according to the diagnosis made after classifying the recorded blood pressure. For example, we display an angry image when indicated a hypertension on the microbit, or we display a sad image for indication of hypertension, and we display a happy image when the blood pressure range is within the normal range. In the fifth feature, the smart heart monitor is able to store and display the previous record of blood measurement. The working logic behind this is that we initially set 2 variables to 0 and 1 variable to a true Boolean value. When the recordings have been done and the system is done with all the diagnoses and warnings, the variable called requirement value is changed to false, which activated the if condition at the end of the while loop to ask whether the user wants to remeasure their blood pressure. If they want, the previous systole and previous diastole variable is assigned to the current systole and diastole value, such that it may be displayed on the OLED in the next measurement. In the sixth feature, we implement automation in the air pumping and air releasing in the Sphygma manometer. Since we already connected to the air pump pin and the air valve pin to the microbit, we are able to send signals from it to actuate the pumping and releasing. The pumping is triggered when the user presses at the start, in which it will start to pump for 5.5 seconds and will stop pumping after that. The air will be released fully after the whole diagnosis has been done, which can be seen from the code pin2.write digital zero function. After this experiment, we have several suggestions for people who want to pursue more or continue the system to improve its overall functions. One of which is to implement wireless control of blood pressure monitor. Second is to add error handling to reduce inaccuracy of measurement due to external factors such as unnecessary movements from the arms that is being tested on. And the third one is to compute heartbeat and detect systole and diastole manually. In conclusion, the smart heart monitor is designed to automatically pump and release air from the sphygmomanometer. Although users have to record it manually from the cuff blood pressure graph plotted, the smart heart monitor is able to classify those detected blood pressure into 3 different diagnoses, which is hypotension, normal, and hypertension, and therefore give different kind of messages accordingly through different kind of actuators. The system is also able to record the previous systole and diastole to be displayed in future measurements, so the users can compare their current blood pressure measured and the previous one. So this is the working principle behind our. Here, when button A is pressed, the sphygmomanometer is automatically pumped. Here, we need to record it manually by pressing button A and button B and based it on the graph plotted from the MIA. Here, users are given the chance to remeasure their blood pressure. And here, as you can see, the previous systole and diastole from the last measurement was recorded and displayed in current recordings. When we don't want to retest again, the system will end and it will break out of the while loop. These are the references that are used for this presentation. Thank you very much.
Thank you very much.
Thank you very much.